Hi, my name is Rohan Prabharam, and this is my Physics 2212 Lab 2 presentation on the magnetic field of a bar magnet. In this lab, we examine how the magnetic field changes with distance and orientation relative to a small permanent magnet. In this experiment, we use a smartphone magnetometer app to measure the magnetic field at various distances both along and perpendicular to the magnet's axis. The goal was to analyze how the field varies spatially and determine if it behaves like a magnetic dipole. We also estimated the magnet's dipole moment and verified the inverse cube relationship between field and distance. So the lab is based on two key physics principles: the Biot-Savart law, which gives the magnetic field due to a moving charge or current, and the magnetic dipole field model. For a bar magnet treated as a dipole, the field along the axis follows a 1 over r cubed dependence. This gives us a way to verify theoretical expectations through data fitting. So, the procedure for this lab was to ensure accurate readings. We first aligned the phone to cancel Earth's magnetic field in the x direction. We found the phone's magnetometer chip location by sliding it until the field peaked. We then collected data at 2, 7, 12, 17, and 22 centimeters from the magnet, repeating each measurement 3 times and averaging. Measurements were taken both on axis and perpendicular to the axis to compare vector behavior. So looking at the on-axis data analysis, so the magnetic field strength dropped rapidly with distance. So by transforming the data into a logarithmic form and plotting ln b versus ln r, we found a slope of negative 3.05. The y-intercept gave us the constant needed for calculating the magnetic dipole moment. So looking at the shred spreadsheet, so this graph shows the on-axis data in logarithmic form with a linear fit. The strong correlation confirms that our measurements follow a power law relationship. Minor deviations are likely due to sensor misalignment or ambient noise, but the trend is consistent across trials. So looking at the magnetic moment, using the slope and intercept from the log-log plot, we calculated the constant K and then plugged this into the theoretical formula B. We solved for the dipole moment, which is about 4.82 am squared. This was consistent with the expected range for a small bar magnet. So looking at the off-axis data and the field comparisons. So off-axis measurements at the same distance gave smaller and more variable field values. As predicted, the field perpendicular to the magnet is weaker and not directed along a single axis. This highlights the importance of vector combination to fully understand the spatial field structure. And here are the measured components: B net, B model, and the error. So we used GlowScript VPython to simulate the magnetic field of a dipole. The magnet was represented as a cylinder, and we programmed the dipole magnetic field formula using vector math. This allowed us to visualize the 3D field with arrows at multiple points around the magnet. Given here is the output of the code. And this screenshot shows the main code used for the simulation. The dipole B function calculates the magnetic field based on the position vector and the dipole moment. We placed observation points on axis perpendicular and at 45 degrees to visualize differences in direction and magnitude. So at a point 45 degrees from the magnet's axis, the simulation showed a field vector that was neither aligned with aligned with x nor y, confirming the need for full 3D vector treatment. The result matched expectations. The field was weaker than on axis, but still followed dipole behavior. So, looking at some assumptions and sources of error, we assume the magnet behaves like a pure dipole in the far field, and that the Earth's field was constant. Errors may have come from inaccurately estimating the phone chip location or electromagnetic interference of the lab space, and small misalignments during measurements also can contribute to variation. So, looking at our observations, the field is strongest near the magnet and falls rapidly with distance. The on-axis field is stronger and more directional than off-axis, and at large distances as bx approaches 0, which confirms dipole behavior. And we got a log slope of negative 3.05, which confirms our theoretical expectations. So in summary, this experiment confirmed that a small bar magnet produces a dipole field in the far field. We successfully used experimental data to calculate the dipole moment and verify the theoretical exponent of negative 3 for the distance dependence. The code-based simulation also reinforced our physical understanding by accurately visualizing the direction and relative strength of the field vectors in space. Thank you.